Hello students, in our previous video we learnt about the first decomposition theorem. Now we shall learn about the second decomposition theorem. The theorem states that for every fuzzy set A element of the set of all fuzzy sets under the universal set X, A is equal to union of special fuzzy set A for alpha an element of closed interval 0, 1. The special fuzzy set is with respect to the strong alpha cut, where special fuzzy set with respect to strong alpha cut denotes a special fuzzy set. That is, this is the denotion for the special fuzzy set with respect to strong alpha cut, and this is given by strong alpha cut A of x is equal to alpha multiplied with strong alpha cut of A of x, and the union denotes the standard fuzzy union. We shall now see the proof of this. Now, the proof of this theorem is analogous to the proof of the first decomposition theorem. So, we shall see the proof now. So, first we are going to take some particular value. So, for each particular value x, which is an element of capital X, we are going to consider the membership grade of X with respect to the fuzzy set A to be equal to A. So then we know that if this is the membership grade, we can write the union of all special fuzzy set A with respect to the alpha cut set, strong alpha cut set, where alpha is an element of closed interval 0, 1 of X, can be written as supremum of strong alpha cut of A of X and alpha an element of closed interval 0, 1. This is the supremum of this set. Because it is union, we know that it will be maximum, and because we are having many sets, we are going to take it as supremum of, and this can be written as maximum of. We are going to split this interval. Now how are we going to split this interval alpha, which is between closed interval 0, 1? Let us see. So first what we are going to do, we are going to consider the special fuzzy set where it is going to be between 0 and A, where we are not going to include A. So it is excluding A, and so I am having the open interval over here. And the supremum of the special fuzzy set A of x with respect to alpha, strong alpha cut. Now here we are going to take alpha to be an element of closed interval A, 1. That is, we are going to include this A. So here alpha is an element of closed interval 0, open interval A, and here alpha is an element of A, 1. So this 0, 1, the interval 0, 1, we are going to split it in this way, where this A is somewhere in between 0 and 1. So now let us mark this as equation 1. We shall evaluate these two separately and we can substitute here. So first we shall evaluate this. So while finding this, now here first let us assume, consider, let for each alpha an element of closed interval 0, 1. So because we are taking closed interval 0, A, 1, I'm sorry, the closed interval A, 1, we have. Now because this is an element of this, now we can imagine it. So this is 0 and this is 1. A is somewhere in between this. Now alpha is an element of closed interval A, 1, which means alpha lies somewhere here. So it lies in between A and 1. It includes A because we are considering the closed interval. So we have here alpha to be greater than or equal to A. And so we can write this as A is lesser than or equal to alpha. Now what is A of x? A of x is equal to A, and this A is lesser than or equal to alpha. So we can say that A of x is lesser or than or equal to alpha, which implies x is not an element of strong alpha cut because it is equal, we are having lesser than or equal to, x is not an element of strong alpha cut of A. So if x is not an element of strong alpha cut, then the special membership function with respect to alpha, strong alpha cut will be equal to 0, because we know that if it is not an element, it has to take the value 0. And so from this we can evaluate the special fuzzy set A of x, which is equal to alpha multiplied with strong alpha cut of A of x. So that is equal to alpha multiplied with this value is what? It is 0. So that is equal to 0. Therefore supremum of special fuzzy set A of x and then alpha an element of closed interval a comma 1 is equal to 0. And so let us mark this as equation 2. So we have evaluated this and this we have found it to be 0. Next we shall evaluate this. So now to prove this we have to consider for each alpha element of closed interval 0 comma open interval a. So this will imply that we have alpha to be lesser than a because we are not including a. So for example this is 0 and 1 and somewhere here we have a. So we are considering closed interval 0 and open interval a. So our alpha will be somewhere here. So it will be surely lesser than a because we have excluded a. It will be definitely lesser than a. So this can also be written as a is greater than alpha. So from this we can say that a of x is equal to a, which is greater than alpha, and so this will imply a of x is strictly greater than alpha. Now if a of x is strictly greater than alpha, we can say that x belongs to the strong alpha cut of a by the definition of strong alpha cut. So now if x is an element of strong alpha cut, then the special membership function a of x, okay, strong alpha cut of a of x will be equal to 1. This is by the decomposition of a fuzzy set. We have already seen. So special this is about the special membership function, and so strong alpha cut of a of x will be equal to 1. Now we shall evaluate the special fuzzy set. So special fuzzy set a of x with respect to strong alpha cut will be equal to alpha multiplied with strong special membership function, okay, of a of x, and so that is equal to alpha multiplied by 1, which is equal to alpha. So this is multiplied by 1 because the value of this is equal to 1, and so that is equal to alpha, and therefore we can say that the supremum of alpha strong alpha cut for alpha an element of closed interval 0 comma a is equal to, we shall substitute alpha in this place. So we can substitute alpha instead of this. So this will be equal to supremum of alpha element of closed interval a comma open interval thus and alpha. But now what is the supremum value of alpha in this? We have excluded a, and so the value of alpha will be lesser than a, as I showed you here. And if we consider this interval to be a very less quantity epsilon, so this can be a minus epsilon because it is lesser than a. It is some value we have to subtract from a, and we choose that value to be some minor quantity, and so that is a minus epsilon, a very insignificant quantity epsilon. And so this can be written as so this will be equal to a minus epsilon, and this will be equal to a as epsilon tends to 0. So therefore the supremum of the special fuzzy set is equal to a. And what is a? By our consideration from the beginning we have considered it to be a of x. So but we will have it as a, and we will substitute a in equation 1. So this is equation 2, that is supremum of this value is equal to a is equation 2. So substituting 2, this is 3, already we have found 2. So 2 and 3 in equation 1 we obtain. So what do we get? So this is our equation 1. So therefore the union of this set is equal to, so union of, so this one we have to write union of for alpha an element of closed interval 0 comma 1 of x is equal to, now what is this is equal to? Maximum of these two. So that is equal to maximum of Now this we have evaluated already and we have got it as A. So as per this, so this is A. So this is A comma 0, and that will be equal to A only, and that is equal to A of x. So therefore generally this is for one particular value x, and so we can say this generally also. So union of alpha and element of closed interval 0 comma 1 plus of A is equal to A. So we have proved. Hope you have understood the second decomposition theorem also. Thank you. And the proof of the third decomposition theorem is absolutely analogous to the proof of the first decomposition theorem and the second decomposition theorem as well. So you can try that and you can finish the proof of the third decomposition theorem. You can take it as an assignment. Thank you.